Hello, everybody, and welcome to the first episode. Today, I'll be introducing the topic of mathematical optimization. The first episode will be a bit academic in nature, but for those new to this topic, the episode will introduce the fundamental concepts and principles that will be essential for future videos. Before we jump into the content, I want to briefly touch on what's covered in today's episode. First, we will start off with what mathematical optimization is and why it is important. In part 2, I will introduce a general approach for solving optimization problems, and in part 3, I will dive into the fundamentals of mathematical models, including their core components, evaluating solutions, and what terminology notation you will need to understand. In part 4, I will bring it all together with a simple introductory problem, then conclude the episode with some brief discussion on references and tools viewers will need and what to expect for episode 2. So with that, let's get started. First, let's talk about what exactly mathematical optimization is and why it is so important to running a business. I describe optimization as a mathematical abstraction of a business problem or business situation. It describes how the business operates in terms of a mathematical relationship or equations, and in doing so enables quantitative decision-making. It is also referred to as decision science, management science, or more commonly, operations research. Optimization is important for any business for a few key reasons. First, many decisions involve a large number of considerations or constraints, often so many considerations that keeping track of them is not possible for an individual. Second, many decisions are often the composite of many smaller decisions, and the combination of possible choices is so numerous it obscures the optimal solution. And finally, making reliable, quantitative, and error-tolerant decisions requires a robust model. Next up is a general approach for solving optimization problems. Any good problem solver usually has a well-developed problem-solving approach. Depicted here is a 6-step process that I use. While this approach has served me well, it is by no means the standard. The first step in solving any problem is developing the opportunity statement. In this step, we clearly state what business outcome we are trying to achieve. It is important to involve key stakeholders when developing this statement, as it could have a major impact on the direction taken to solve the problem. The second step is problem definition. This step is often the longest and involves engaging many different disciplines and functions. This step includes listing required information for the problem, determining which information is available, or if data engineering is required, and understanding the applicable business rules and identifying what outputs will be needed to make a decision. Defining all of this is crucial to translating the problem into its mathematical form. Step 3 is model development. Here, we translate the business problem into a set of mathematical equations. This is the mathematical abstraction process. The accuracy of the model is directly tied to the performance of the first 2 steps. Once the step is complete, we are ready to solve the problem in step 4. With a good model and solver, obtaining a solution should be quick. However, the analysis of that solution can be time-consuming. In reviewing the solution, one must look for nonsensical outputs, which are a good tell that the model was not correctly defined. You have probably heard the saying, garbage in is garbage out. Poor problem definition and model development will lead to poor results. Solution analysis often leads to iterations with problem definition and model development, as discoveries about missing information, missing constraints, or data quality issues are routinely revealed during this step. Step 5 is to implement the solution after validation. Implementation involves carrying out a decision based on the model solution. Implementation also includes developing the right governance and processes to ensure that the benefits of implementing the solution are not lost as a result of poor execution. And finally, in step 6, we need to sustain and improve our work. Almost all real-world business problems are dynamic and will change over time. Models should strive for robustness. And as the model is used, opportunities for improved functionality will become more apparent. While this process is laid out sequentially, you will find that iterating back to earlier steps is common and expected for almost all problems. And now for part 3, mathematical models. Shown here is a generic roadmap for the life of a problem. On the left and the right, we have the inputs and the outputs from our problem. Sandwiched between them on the left is the mathematical model, and to the immediate right, the solver. Within the dotted box are the core components of the mathematical model. This includes the objective function, the decision variables, and the constraints. These components comprise the entirety of the mathematical model. This model is then passed to a solver, which finds a solution. These final values from the solver are then our outputs and are used for decision making. We will talk in more detail about each item depicted here. The first items to discuss are the inputs and the outputs, as these are the most straightforward. Inputs are generally information used by the model, such as prices of products or costs of raw materials, the pieces of manufacturing equipment, or equipment capacity. Generally, inputs are information known about the business and used in the model, and are also referred to as parameters. Outputs are desired information or the decisions from the model, which collectively represent the solution to the problem. Specific outputs will include the solution value, like the profit or cost, decision variable values, and information on what limited the solution, i.e., what prevented the model from finding a better solution value. The first item, or the first core component of a mathematical model, is the objective function. The objective function is a mathematical equation that quantifies the opportunity statement. It's what the model uses to determine when an optimal solution has been found. And depending on the opportunity statement, it can be maximized or minimized. To explain further, let's consider a simple example. Your business sells two different nutrition bars. One bar is for athletes, denoted A, and takes 20 minutes to make per bar with a net margin of $5 per bar. The other is a breakfast bar for kids, denoted B, taking 12 minutes to make the net margin of $2 per bar. If we want to maximize profit, the objective function would be written as $5 per bar times A, the number of bars made, plus $2 per bar times B, the number of bars made. If we wanted to, say, minimize manufacturing time or cost, the objective function might be written instead as 20 minutes per bar times A, the number of bars made, plus 12 minutes per bar times B, the number of bars made. Again, going back here, you can see that depending on the opportunity statement, the objective function might be written differently. The second component of mathematical models is the decision variables. Decision variables represent all the decisions or choices that must be made by the model. The decision variable values themselves reflect the choices that produce the best objective function value. And taken from the previous example, the decision variables would be A, the number of athletic bars to produce, and B, the number of kids' breakfast bars to produce. And the final component of mathematical models is the constraints. The constraints are the limits placed on the problem. These limits dictate the allowable solutions and cannot be violated. Constraints can be placed on decision variables, limiting the range of possible values, or represented as other conditions. Taken from our previous example, we can impose two hypothetical constraints. The first hypothetical constraint would be that total customer demand for athletic bars is limited to 300 bars. This constraint would be an example of a constraint that might be placed on a decision variable, limiting the range of possible values. The next hypothetical constraint is the amount of time available to produce any combination of bars, and it is limited to 200 hours. This is a constraint of the problem that is not directly placed on the decision variables, but will impact the decision variable values. Now that we've defined the core components of our mathematical model, the next step is to solve it. And to do this, we enlist the help of a solver. So what exactly is a solver? A solver is an algorithm or method used to find a solution to a problem. Our job is to build the model, and the solver's job is to find the best solution. There are many types of solvers. Examples include CVC or Cplex, and their applications can be problem specific. With the core components of the mathematical model covered, let's now turn our attention to the topic of solution and sensitivity analysis. Solution and sensitivity analysis is often what differentiates a good analyst from a bad analyst. A good analyst will understand the solution apart from just the numbers and be able to convey the strategic themes derived from the solution. They can speak to the underlying drivers of the solution, such as how recent changes in pricing or demand are influencing outputs, and they can articulate what is constraining the problem from achieving a better solution. Naturally, this takes practice, but it starts by spending time understanding the solution. Conversely, just pushing a button and taking whatever solution comes out as credible can have disastrous results for the business. To illustrate this, I just want to share a personal anecdote. In one of my first positions as a LP planner, where I was running a fairly large and complex mathematical model, I was responsible for generating a operational plan on a weekly basis for the facility. And essentially my job was to determine which pieces of equipment were going to be in operation and what kind of products they were going to be producing. And that was all influenced by raw material pricing, capacity limits on each piece of equipment, as well as product pricing. And in one of the first meetings where I shared my run plan, one of our senior leadership team members asked a question because some of the economics did not make sense, to which I replied, well, that's what the model told me. The feedback I got promptly after that meeting from my supervisor was that they weren't paying me a lot of money to click buttons and run a model, but they were paying me money to understand the model and understand the constraints and the effects of pricing, both from a raw material and product standpoint. So again, if you want to be a good analyst, spending time understanding the solution and the model and how the different inputs influence the outputs is really the way to go. With that said, the first step in any solution analysis is always to check for reasonableness of the outputs. And by reasonableness, I mean you want to look for extreme values. Some simple examples, if you go back to the producing, let's say, the nutrition bars. If on any given week throughout the year, we've never produced more than 500 bars of either type A or B, and we have a solution that says we're going to produce 1.5 million bars of A, that's clearly an indication that something is wrong. So you want to look for these sorts of extreme values or nonsensical outputs. This is a great way to catch any early red flags. And you'll see this happen a lot as you practice more and more with complex problems, because it's pretty easy to make small mistakes with inputs or constraints that will lead to these nonsensical solutions. Once we've sort of validated that the solution looks reasonable and we're confident that it's something we can work with, the next step is sensitivity analysis. Sensitivity analysis is the practice of determining over what range of inputs the optimal solution remains valid. This is crucial to understand when the solution may no longer be valid due to changing inputs. It allows us to make a determination when to rerun the model and to find a new solution. Oftentimes, you'll spend days or hours running a complex model to get a solution. And quite frankly, the pricing environment may be changing faster than that. And understanding the differential between different prices or different inputs and over what range your solution is still valid is really important to enable making quick decisions on the fly. There's other elements to sensitivity analysis that we'll discuss in more detail in future videos as we work through example problems. But that is basically the gist of it. And now for our final topic regarding mathematical models, we will turn to terminology and notation. Shown here is a set of common terms that are used in optimization that you'll need to become familiar with. The first term here is right-hand side, or RHS. And right-hand side is defined as the limiting value used on the right-hand side of a constraint. For example, if we were to take a hypothetical constraint, 2a plus 3b is less than or equal to 10, the right-hand side, or RHS, in this case would be 10. The next term is coefficient. Coefficient is the numerical multiplier used to relate how two or more variables change in relation to each other. The coefficients in the constraint of 2a plus 3b are less than or equal to 10 are 2 and 3 respectively. The next two terms are slack and surplus, and these are related to constraints. So for a less than or equal to constraint, like the 2a plus 3b less than or equal to 10, the slack would be the difference between the right-hand side and the left-hand side values. So for example, if we assigned a value of 1 to A and 2 to B, we would have 2 times 1 plus 3 times 2 equal to 8, which is less than or equal to 10. And we could say that we both satisfied this constraint, and we also had a slack of 2, since the difference between the right-hand side of 10 and left-hand side of 8 is 2. Surplus is the converse situation where the constraint is a greater than or equal to constraint. So if we just flip that sign around for the 2a plus 3b greater than or equal to 10 and assigned a value of 4 to A and 2 to B, we would have 2 times 4 plus 3 times 2, which is 14, which is greater than or equal to 10. So again, here we're both satisfying the constraint. And if we take the difference between the right-hand side and the left-hand side, we would say that we have a surplus of 4. The next term is dual value. It's also called limit cost or shadow price. On this channel, I'll probably use the term limit cost more often because I think it's a little bit more intuitive and it better expresses what the meaning of the term dual value is. But this applies to constraints. So if you have a problem where a constraint is limiting, the dual value reflects how much the objective function improves for a single unit of change in the right-hand side. If the constraint is not limiting, then the dual value is 0. So another way to say this is if you have a constraint where you have slack or you have surplus, then the dual value for that constraint is 0 because it's not limiting your problem. But if you have a constraint that is limiting the problem, so if we take the case of 2a plus 3b less than or equal to 10, If that value of 10 is limiting the solutions and the values of A and B, then that constraint would have a dual value or limit cost associated with it. And that value, let's say it's 4, would mean that for an increase of 10 to 11 on the right-hand side, we could improve our objective function by 4 units. The last term here is reduced cost, and this is related to decision variables. If a decision variable is 0, then it will have a reduced cost that reflects the needed change in its objective function coefficient in order for it to obtain a positive non-zero value. If a decision variable is positive, the reduced cost is then 0. So similar to dual value, if you have a decision variable that is 0, meaning the model and the solver have decided not to do anything with that decision variable, then it will have a reduced cost. And that reduced cost is the change that would be needed in its objective function coefficient in order for it to be non-zero and positive. But if a decision variable takes on a positive value, then it will have a reduced cost of 0. So if we had a decision variable that had a reduced cost of -1, this would mean that the coefficient needs to be increased by 1. So I know these might be a little abstract right now or hard to conceptualize, but as we do problems, it'll become easier. Next is notation. So there's a lot of mathematical notation out there, overwhelmingly so, but fortunately for us in optimization, there's only 2 that are very common and used often. The first is sigma. So on the left here, you see this weird looking E. This is the Greek letter sigma, and it stands or means the summation of a set of values, variables, or equations, and the subscript I that's below it indicates across which index you're going to sum each value, variable, or equation. So a pretty simple example, if we had a set of numbers, we'll call that set X, and in that set we had the numbers 1, 3, and 5, and we wanted to sum all of those numbers up, which would be 9, you could write sigma X, and that would basically read as sum all the numbers in the set X. The next notation is this weird looking upside down A, which is called for all. And essentially this means to perform or replicate for each element in a set. So as we get into problems, you'll see very commonly that there is a constraint we'll be placing on a set of variables. And the same constraint formula or equation might apply for each element in a set. So instead of writing out multiple constraints, we will write out the formula for that constraint and use this for all notation to indicate that we need to replicate that for each element in that variable set. So to help maybe explain this a little bit better, the reason we care about notation is because as problems get increasingly complicated, the mathematical notation is going to allow us to save a lot of time and space when we're writing the model out. We'll be able to do it in a succinct and abbreviated manner. And this will translate into coding, which is important, because as you start to code bigger and bigger problems in Python, being succinct with your code is going to make it much more readable and accessible and sustainable in the long run. So with that, let's just do a quick example. So again, let's consider a hypothetical problem where we are trying to optimally distribute various products to warehouses. So in this model, we will impose a constraint on how much total product each warehouse can receive. So we'll start with some definitions. So we'll let I here be the set of products. So I is going to be equal to include a set of products. We'll call them products A, B, C, D, and so on. We'll let J be the set of warehouses that can receive these products, and we'll abbreviate these warehouses with their location. So we'll have Phoenix here as PHX, San Francisco as SF, and Denver is DN, and so on. And so J will be a set of warehouses. We'll let X sub IJ, so we have 2 subscripts there on X, I, and J, and we'll let X sub IJ be the number of products I that are shipped to warehouse J. And we'll have C sub J, and we'll let C sub J be the maximum capacity for products at warehouse J. So C will represent the maximum number of products that can be received and stored at a given warehouse. So if we wanted to write each constraint out, we could do that. But if we wanted to use mathematical notation to write this succinctly, we could do it as follows. We could say we have a warehouse capacity constraint, and we'll define that as sigma sub I of X sub IJ has to be less than or equal to C sub J. So that means for each product I going to warehouse J, the sum of all of those has to be less than or equal to the capacity of warehouse J. And this constraint has to be done for each warehouse, which is why we have at the end here the for all sub J. So we would basically replicate this constraint for each of the different warehouses. So I know that that might be somewhat confusing, but again, this will become a lot easier the more we practice this in example problems. And with that, we are going to jump into our first introductory example problem and try and bring all of this together. We are going to be doing a problem from a book called The Introduction to Management Science, Quantitative Approach by David Anderson. And this will be problem 14 in chapter 2. So shown here on the left is a description of the problem that was referenced in the previous slide. Here we have a company, RMC Incorporated, which is a small firm that produces a variety of chemical products. In one of their production processes, they use 3 raw materials that are blended or mixed together to produce 2 products, a fuel additive and a solvent base. Each ton of fuel additive is a mixture of 2/5 of a ton of material 1, 3/5 of a ton of material 3, and a ton of solvent base is a mixture of 1/2 of a ton of material 1, 1/5 of a ton of material 2, and 3/10 of a ton of material 3. After deducting costs, the profit contribution is $40 per ton of fuel additive and $30 per ton of solvent base. RMC's production is constrained by a limited availability of the 3 raw materials. For the current production period, RMC has available the following quantities of each raw material: 20 tons for material 1, 5 tons for material 2, and 21 tons for material 3. So if you recall our problem-solving approach, our first step is to write an opportunity statement. And based on what I read, I wrote the following: maximize profit by determining how much of each product, solvent base and fuel additive, to produce with the raw materials that are available. Now that we've got our opportunity statement, the next step is problem definition. Now, this is a pretty simple problem, obviously, because we're trying to just introduce some of the concepts. So a lot of what the problem definition will be here is a restatement of the facts and maybe an inference of some other parameters that weren't explicitly stated. In a more complicated problem, oftentimes you're not going to have all the definition you need from a simple problem description like that. And it will be incumbent on the problem solver to seek that out from customers, stakeholders, other functions, and other disciplines. But from that problem statement, we're able to state the following. We produce 2 products, solvent base and fuel additive. We know solvent base generates a profit of $30 a ton and fuel additive generates a profit of $40 a ton. We know that each product can use up to 3 raw materials 1, 2, and 3. We know that 1 ton of solvent base requires 1/2 a ton of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. And we know that a ton of fuel additive requires only 0.4 tons of material 1 and 0.6 tons of material 3, and no material 2. We want to maximize profits for a single period. We're not considering any multi-period sales. And we know the raw material availability is limited to 20 tons of material 1, 5 tons of material 2, and 21 tons of material 3, and that we cannot purchase or procure any additional raw materials. With our problem definition complete, we can move towards model development, where we will write down the mathematical abstraction of our problem. And we'll start with a couple definitions. We're going to let S be defined as the tons of solvent base produced and sold. We're going to let F be the tons of fuel additive produced and sold. We'll define our objective function to maximize profit. Profit will be defined as $30 per ton times S plus $40 per ton times F. Our decision variables here are S, the tons of solvent base produced and sold, and F, the tons of fuel additive produced and sold. And we'll have 5 constraints. 3 of those are material balance constraints. So we know that the total consumption of material 1 has to be less than or equal to 20. So 0.4 tons of material 1 for every ton of F, plus 0.5 tons of material per every ton of S produced has to add up to less than or equal to 20. And similarly for material 2 and material 3. And finally, we have a non-negative bound placed on F and S. They must be greater than or equal to 0. As we know, we can't take on negative values for these products. And if you look at the solution to this problem, what you end up getting is an objective function of $1,600. We would make 25 tons of fuel additive and 20 tons of solvent base. We would consume all of material 1, all 20 tons. We would consume 4 out of 5 tons of material 2, and we would consume 21 tons of 21 tons, or all of material 3. And on the right here, we have an output of sensitivity analysis that is obtained from Excel. And essentially what you can see here is on this top variable cells value, we have our final values of F and S of 25 tons and 20 tons. And essentially we have an allowable increase here and an allowable decrease here for the objective coefficient. So putting this together, what this says is that we know we make $40 a ton for every ton of fuel additive we produce. And we know we make $30 a ton for every ton of S, or solvent base, we produce. And the optimal solution is 25 tons and 20 tons respectively. Now, the allowable increase and decrease represent how much this coefficient can change upwards and downwards before the 25 and 20 solution is no longer valid. So if this objective function went from 40 to 50, or went from 40 to 30, the optimal solution would still be 25 and 20. And likewise, if the objective coefficient for solvent base went from, let's say, 30 to 40, or 30 to 25, the optimal solution would remain 25 and 20. But if these objective coefficients, if the pricing of these products changes beyond the values listed here, then this 25 and 20 optimal solution is no longer valid. And that's how you read this part of a sensitivity analysis. Similarly, we have sensitivity analysis for constraints, right? So we have our final value, this is essentially 0. If you read this, this is negative 3.7 times 10 to the negative 14th, which is in all cases 0. Similarly, for material 3, the final value is 0. This is essentially means that we've consumed all the materials. As we stated earlier over here, we have 1 excess ton of material for material 2. And what you see here is the shadow price. I mentioned earlier, dual value, limit cost, or shadow price are all interchangeable. And because we consumed all material 1 and all material 2, those are actually constraining the problem. So if we had more material 1 or more material 3, we could make more product, and therefore we would have a higher objective function than 1600. So how would that objective function change if I had an additional ton of material 1? Well, my objective function would go up by $33.33 for every additional ton of material 1 I had available. So if this went from 20 to 21, this would go from 1600 to 1633.33. Similar, if I had an additional ton of material 3, 22 instead of 21, I would consume it, and this objective function would go from 1600 to 1644 and 44. The constraint on the right-hand side, which is again 0, and not to confuse anybody, but if you move this 20 over here and you had 0.4 F plus 0.5 S minus 20, that's how you would have the right-hand side. So it's essentially just rearranging that constraint in Excel. And I'll show that here in a little bit. But there's also an allowable increase and allowable decrease. So changing that right-hand side constraint, right, whether it goes up by 6 or down by 1.5, won't affect the information shown here in terms of the shadow price. But if you were to say, I don't know, go up by 8 on material 1, then this shadow price is no longer valid. Similarly for material 3 constraint. So if I went from 20 to 25 tons of material 1, the incremental improvement of the objective function by this shadow price would be valid. But if I went from 20 to 30 tons of material 1, this shadow price would not hold up beyond 26 tons. And the same goes for the allowable decrease, and the same goes for the material 3 constraint. So I know that's a lot to take in, from the mathematical abstraction to the solution and how I got here. And now I'm gonna take us away from the PowerPoint and into Excel, where I'm gonna demonstrate how you can solve this problem using 3 different methodologies, which will include using Excel's built-in solver and using a mathematical abstraction of equations. We will also show how to do this graphically using a plotting different constraint lines and objective functions on a graph and looking for where to find the optimal solution in what's called the solution space. And a third method doing what's called a rows and columns matrix, which is basically a different way to represent the mathematical model. So with that, we'll jump over to Excel and I'll walk through how to solve this problem using Excel. All right, so here is the Excel solution file I'm going to cover. So we've got 3 solutions here. I've got a mathematical model that we'll solve using Excel's built-in solver capability. I've got a graphical solution. I've got a solution using a matrix setup, also using a built-in solver capability, and I have a sensitivity analysis report that I will go over. So this first method for solving this type of problem using Excel is to set up the mathematical model that we just reviewed in the PowerPoint in Excel. So the first element here is this objective function. So I've set this up as E6 times E8 plus E5 times E7, which is essentially the amount of F and S we make times their coefficients in the objective function respectively, $40 and $30 per metric ton. I've also included here the values or the available amounts of material 1, 2, and 3. And down here, I've also written out the material constraints for 1, 2, and 3. And you'll notice I've written them out slightly differently than I did in the PowerPoint. If you recall in the PowerPoint, I had 0.4 times F plus 0.5 times S less than or equal to M1 or 20. In this case, what I've actually written here, and I just noticed a small typo, is I've moved that right-hand side value, which was the available material. I've actually moved that over to the left-hand side. So essentially what you would have instead is something like 0.4 times F plus 0.5 times S minus that 20 has to be less than or equal to 0. So it's very similar to what we wrote. We just moved this value over to the left-hand side. And so I know that I have to be less than or equal to 0, which means that the total amount of material 1 consumed, defined here, has to be less than or equal to 20, which is said similarly as saying that this minus 20 has to be less than or equal to 0. So it's written slightly differently here. It's the same constraint, and I'll show you why we do that in Solver, because it just sets it up a little easier. And so that's how these are written. And so in order to solve this, once you've set this all up, you go to the solver function, you pick your objective function cell, which here is E4, you select maximization, which is, we know from our opportunity statement, you select the range of cells that represents your decision variables, which here is E7 and E8, so F and S. And then we set up the constraints. Again, we have 5 constraints, 3 of these, E12, E13, and E14, here, here, and here, are material balance constraints, and these all must be less than or equal to 0, meaning that the materials consumed by the amount of F and S made must be less than or equal to the amount available. And we've got E7 and E8 must be greater than or equal to 0, so these are just the non-negative production constraints we placed on our decision variables. Down here is a select a solver method dropdown. This is read as select your solver. So there's 3 built-in solvers, GRG nonlinear, which we'll use when we get to solving nonlinear problems in Excel, but not necessary here. Simplex LP, which is probably the most popular one and well-known simple solver for linear programs, and then evolutionary, which you probably won't use much. There's some options here, I won't go into them, but essentially once you've got this all set up, I would always check make unconstrained variables non-negative unless you have a really specific case where decision variables can take on negative values, which is rare. And then you can go ahead and you can click solve, and it's going to spit out the solution, which I've already done here so you can see. It will say solver found a solution, all constraints and optimality conditions are satisfied. So that's a good sign. If you just want to get the solution, you can click OK, keep solver solution. There's some reports over here that are useful. So sensitivity, which I'm going to talk about in a minute. If you click sensitivity and click OK, it'll generate a sensitivity report. I'm not going to do that now because I already did it, and I'll show you that in a second. But essentially, this is a really handy feature for Excel. So that is how you would solve it using this method. And to jump over to the sensitivity report, This is what I already showed you in the PowerPoint, but just again to elaborate, we have variable cells section, which is the decision variables sensitivity analysis. We have our optimal solution pair, 25 and 20. We have their objective coefficients, the profit per ton, and the allowable decrease and increase of this objective coefficient for which this final value solution pair is valid. So again, if this objective coefficient went from 40 to 70, this would no longer be valid. But as long as the objective coefficient changes upwards or downwards within these allowable ranges, this optimal solution pair holds. Similarly, for constraints, you have your shadow pricing, which is based on material 1 and 3, which are constraining the problem. And if we were to alleviate those constraints by 1 unit, this is the shadow price that we would realize in the objective function, an increase of $33.33 for material 1, $44.44 for material 3. And those shadow price increases are valid over this range. So if material 1 were to go up or down within the allowable increase and decreases, the shadow price holds true. Same for material 4, but outside of these allowable increases and decreases, the shadow price listed here is no longer going to be the case. And as you can see up here, one thing I want to come back to, reduced cost. So I talked about in the PowerPoint that if a decision variable takes on any positive value, it'll have a reduced cost of 0. This is supposed to reflect the required change in the objective coefficient for the final value, if it's 0, to take a non-zero positive value. So let's just illustrate this. If I go back here and let's say that I am losing, let's say that this is only worth $1 a ton. Okay, not very profitable. I solve this problem again using my solver. I end up making no solvent base and all fuel additive. If I go back to the if I solve this again and make a new sensitivity report, let's do that now. What we'll find is that this decision variable S actually now has a reduced cost. And so this reduced cost is minus 19. So that means this objective coefficient of 1 would need to be increased by 19 in order for S to take on a value positive that is non-zero. So it'd have to be at least $20 per ton. So that's, again, how you would use reduced cost in solution analysis. We'll delete this. I'll return this to its former solution. And with that, we'll move on to graphical analysis. So graphical analysis is great for conceptualizing certain principles, but in practicality, you can almost never use this to solve complicated problems because there's so many dimensions that graphing it is literally impossible. But for this simple solution, we can have a graphical solution, and it's worth at least exploring with you for, again, understanding the concepts. So what I have here is I have an objective function line, and I have my 3 material constraint lines. Material 3 constraint line is dictated by the relationship we have of the available material 3, as well as the definition of how F and S consume material 3. So if you come back and look here, I have S, I have some values of F listed here, 0, 5, 10, all the way up to 35. And then based on the available materials, which I've hidden over here, but we know 20 tons of material 1. We know that whatever we consume of F is going to be 0.6 times F. So if we subtract that and then we divide by the coefficient for S to get the number of S we can make. And as you can see, if we make 0 F, we can make 70 S. And this is all based on a material 3 constraint. And so that's what this line represents. This line shows the maximum value of S you can make for each value of F that you make. And we do this again for material 1 and material 2. And what's interesting is you see that these lines intersect at a few points. And what this creates is called a solution space. So everything that is within this boundary is the solution space. And that means that any pair of F and S that falls within the solution space is a feasible solution. It may not be optimal, but it is feasible. And so what this means is that from 0 to 18.75 metric tons of F made, you can make up to the M2 constraint or 25 tons of S. And M2 is controlling for that range of F. As we make more F beyond 18.75 and up to 25, the controlling or the constraining material is M1. And you can see that this line is below both the M2 and M3 constraint, and therefore controlling the solution space. And then about 25 tons of F, the M3 then controls the solution space, and it becomes a controlling material constraint. And so this solution space is made by these three constraint lines. So how then do we know where the optimal solution is? Well, if you haven't intuited it yet, it's going to be at typically one of these intersections. So what you can do here is take this line of F that represents this line right here for each of the controlling points. So 0 to 1875, and then from 1875 to 25, and then 25 to 35, we know that M2, 1, and 3 are controlling respectively. We use those equations to get our FS pairs, and then we know the dollars per ton we make of the FS pairs, and we can plot an objective function and find the maximum point on that line. So you can see here the maximum point of the objective function line is right here, which is at F equals 25, which happens at this solution space intersect, which is F equals 25 and S equals 20. So without using solver, we can go ahead and find the solution graphically. And then finally, we have the matrix setup. So here it's similar to the mathematical form, but slightly different. We create essentially columns, which we are going to call decision variables. So we have our products, F and S, and our materials that we're going to use, M1, 2, and 3. And these all represent decision variables that can take on a value, and those values are listed here. These values are not necessarily, but can be bound by a lower bound and an upper bound. Well, we know that we can't have negative values for any of these decision variables. Therefore, we are going to put 0 for the lower bound. We have no upper bound on F and S, but we do have upper bounds on the materials of 25 and 21 respectively. And also here is the objective. So we know that we have an objective coefficient for F and S in our objective function. It's $40 per ton of profit for F and $30 per ton of profit for S. We have not imposed any objective function coefficients for materials, but you could have objective function coefficients listed here if, say, there was some sort of penalty of using material 1, 2, or 3 that you wanted to reflect. And then down here is essentially the matrix, the rows of the matrix. And so what we have down here is the constraints. So think of columns as decision variables and rows as material balance constraints. So we know that for every ton of F, we're going to consume 0.4 tons of material 1, 0 tons of material 2, and 0.6 tons of material 3. For every ton of S we make, it's going to be 0.5, 0.2, and 0.3 tons of materials 1, 2, and 3 respectively. The coefficients here are negative because we're representing a consumption of materials 1, 2, and 3. And then in order to do a material balance for material 1, we know that whatever material 1 we decide to provide up to the upper bound, this will reflect the consumption of material 1. And so we use this coefficient, matrix coefficient of 1 to reflect how the material 1 we do balances with the F and S we make. So for every ton of F and S we make, we use these coefficients to reflect the number of material 1 consumed, and we use the coefficient of 1 to reflect the amount of material 1 required, and this must balance to 0. This is the material balance. So these are all equal to 0. And we do that for material 2 and material 3. We use solver as well to do the same thing. We set up slightly differently, as I mentioned, because we're considering materials are going to allow to be decision variables. We can use simplex, solve it. You get the same solution as before. And the right-hand side, same objective function as before. So a different way to do it, a different take. But as you'll find, this is pretty common. There's a lot of folks who prefer this approach. And that represents the 3 methods. So with that, we'll jump back and wrap up the presentation. All right, so now to just wrap up this episode, I'm just going to touch real briefly on some references and tools that you'll need and talk a little bit about what's to come in episode 2. So in terms of references, I already introduced it, but An Introduction to Management Science, Quantitative Approach by David Anderson is a great book, especially if you're looking for additional problems to practice. But the problems that I'll be using to set up some of the discussion on this channel will come from this book. Some of the problems will be problems that I create, or sort of variations of problems I've encountered in my career. And then optimization with PuLP, this website down here, I will put a link in the description of the video, is going to be very helpful for PuLP in terms of referencing the different classes and elements of the library. Tools you'll need. So Anaconda Distribution is great. I'll put a link to the community free edition, but download it. If you got questions about it, there's tons of resources online, so I'm not going to go over that here, but it's the easiest way to get started, in my opinion, with Python, and specifically with this next tool, which is Jupyter Notebook. It will come with that distribution, and that's how I mostly deal with programming in Python. For really advanced cases where people are trying to develop a professional enterprise grade tool and put it into production, there's a whole suite of other methods and tools to use, but for the sake of this channel, to build the capabilities and concepts that people can use at work, we're just going to stick with tools that are free and accessible. Excel will be a good tool, both because we'll be using it for essentially to act like a database or data storage for a lot of the problems. And then when we get to some more complicated, complex problems that may have more sophisticated applications, I'll be leveraging a local instance of MySQL just to demonstrate how you might interface with an enterprise SQL database. In terms of what's coming up for episode 2, so my plan for episode 2 is to introduce Python in the PuLP package for building LP model and how to solve using Python, using some open source free solvers like CBC. And that'll be the intent of episode 2. I will be using the same problem that we used for the introductory example here in that episode. So it won't be totally new, but it will show you how to solve it, but really a fourth way using Python and PuLP. So thanks again for tuning in, and I hope you enjoyed it. Questions or comments, contact the channel email. Until next time, take care.